This will be a brief and hopefully helpful overview of the most important detectors typically found in a nuclear laboratory, with a special emphasis on what we have. To narrow things down a bit, I'll focus only on the detectors used to measure the classic radiation types like alpha, beta and gamma radiation. Sure, we also have X-rays and UV-Vis detectors, but this is not the main focus for today. There will be a deep dive into every single detector, and some of them are already available for a few types. We categorize detectors into three main groups: semiconductors, scintillation counters, and gas-filled detectors. Each of these has subcategories. For the semiconductors, we have lithium-drifted germanium, high-purity germanium, and surface barrier silicon detectors. Scintillation counters include those that use solid scintillation crystals and those that use liquid scintillation cocktails. Gas-filled detectors are categorized by their operating voltage, and there we classify the ionization chamber, proportional counters, and Geiger-Müller counters. Let's start with the Geli versus high-purity germanium. Both are used for gamma spectrometry and thus are unsuitable for measuring alpha and beta radiation. Both use a semiconductor crystal. In this case, it's mainly germanium. A brief excursus when it comes to semiconductors, as this knowledge will be important later. A semiconductor is a material with electrons. Surprising. What's characteristic is how these electrons behave. In a conductor, like metal, electrons are delocalized, forming an electron gas. Here, energy bands describe the states electrons occupy. We have the valence band and the conduction band. In metals, there is no energy gap between the occupied valence and the unoccupied conduction band. In semiconductors, however, there is a slight energy gap. Electrons must be excited to overcome this gap and to enable electrical conductivity, which can occur with relatively low energies such as thermal excitation. This isn't possible with insulators, where the energy gap is much broader. An example of an insulator is sodium iodide. Wonder why I've chosen that example. Returning to the topic, both Geli and HPGE detectors use semiconductor crystals. Ionizing radiation, gamma photons, excite the crystal, creating electron-hole pairs. Here's the difference. HPGEs require extremely pure germanium to prevent impurities to disrupt these pairs before they can be measured. Because high-purity germanium crystals couldn't be ground in the past, lithium drifting was used to solve this problem. Thus, Geli, germanium lithium detectors, are older than HPGE detectors. The efficiency of both is similar, between 1 to 5%. It depends on the energy. High energy gammas pass right through, while low energies are easily shielded by, for example, the housing. Both detectors must be cooled during measurement, but the Geli must remain cooled in between measurements, which the HPGE does not. This makes the high purity detector more convenient and preferred for everyday use. However, we use a germanium lithium crystal for gamma detection because we have established a cooling system which keeps the detector cold, and once this failed, this will probably be exchanged for another high purity germanium detector. In essence, there aren't really major differences between those two. Now onto the scintillation counters. Gamma spectrometry can also be performed with scintillation counters. While we don't do this in our lab, it's still possible. Now let's compare semiconductors to scintillation crystals. Typically, these crystals are thallium-doped sodium iodide. That's the electric insulator. When a gamma photon hits the crystal, electron-hole pairs are created in numbers proportional to the photon's energy. In a semiconductor crystal, say 1000 electron-hole pairs or excitons are generated by an incoming gamma photon. In a scintillation crystal, due to this larger band gap, only 100 pairs are generated. The error will always be the square root of the count rate, number of pairs, and the square root of 1000 is 31.6, whereas the one from 100 is 10. This means that the semiconductor has a detection error of 3.1% in this case, whereas the scintillation crystal has an error of plus or minus 10%. This explains why the peaks are broadened when using a scintillation crystal. However, the efficiency of a scintillation counter is higher, or rather, not efficiency per se, since both are solid materials with similar probabilities for radiation interaction, but the dead time of the scintillation counter is significantly lower. This is because the scintillation counter produces signals as light and not as electrons accelerated by a high voltage. Electrons can never be as fast as light, which is why the scintillation counters can process more signals. Another difference in the detector material is the proton number. Germanium has an atomic number of 32 versus sodium iodide with the atomic number of 11/53. The phenomenon of pair production occurs with photons of energy above 1022 kiloelectron volts in a nuclear field of an atom. The likelihood of such a pair production occurring increases with the atomic number. As a result, scintillation counters tend to produce a relatively higher 511 kiloelectron volt peak when measuring high energy gammas. Then we have the surface barrier silicon detectors. These silicon detectors is what we use for alpha spectrometry. These consist of a thin layer of gold deposited on a N-type silicon. Oxygen can diffuse through the gold, creating a depletion region. These detectors are excellent for detecting highly charged particles like alphas or heavy recoil ions, which is why measurements should not be taken at the topmost slot. These recoil ions can interfere with the alpha spectrometry. While they could be used for measuring beetles, we don't do that here. A vacuum pump is necessary for alpha spectrometry, but cooling isn't required. Now, how do these scintillation counters work? The general function has already been described. Ionizing radiation hits the scintillation crystals, creating electron-hole pairs. These electrons are excited and, thanks to the thallium doping, emit this excitation energy as visible light. Note, the energy is proportional to the number of electron-hole pairs, thus the light intensity, not the wavelength. The wavelength or the color depends on the scintillator. Here I brought you a list of common scintillation crystals and their wavelength. With a scintillation counters, all of these three classical types of radiation can be detected, but it's not a all-in-one detector. Alphas, for example, can be detected depending on the type of scintillation detector that you use. The first form of scintillation detector was a radium clock hand, where the alpha radiation excited a zinc sulfide-based scintillation crystal, causing it to glow. Gas-filled detectors. These can detect all types of radiation, but have a higher efficiency when it comes to alpha and beta radiation. A simple example is the cloud chamber, where no voltage is applied and gas ionization produces electron-ion pairs. When voltage is applied, these pairs can be converted into electrical signals, with electron accelerating towards the positive anode and the positive gas ions, i.e. argon plus ions, slowly moving towards the cathode. This leads to a higher dead time compared to scintillations or semiconductors. Our Berthold LB122, affectionately called the iron, is a proportional counter. The difference between a Geiger-Müller tube and a proportional counter lies in the operating voltage. In the proportional regions, electrons freed by radiation are accelerated strongly enough to cause secondary ionizations. Impact ionization. Here, it's still possible to distinguish alpha from beta radiation. The counting gas in this example is a butane-xenon mixture. Finally, we have the Geiger-Müller counter, which operates in the Geiger region, where every ionization event causes a complete avalanche of discharge in the counting gas, making it impossible to distinguish between radiation types. This was a very brief overview, but this was just for our beginner students to know some basics about the detectors. Sure, there are other countless designs of detectors and other applications and functions and whatnot what I could have delved into, but for this overview I think that's enough. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, thank you for your attention and goodbye!